All right, as you're finishing up that warm-up, we're gonna just start 5 here, building quadratic functions to describe situations. So the training wheels, if you will, are gonna come off a little bit. And now we're gonna get into why quadratics are so important and scenarios where we can visualize a quadratic. First question, study the table. What do you notice? What do you wonder? Anybody wanna have a quick comment there?
It's quadratic.
Which one?
The table, it's quadratic.
Yeah, the y's might be going up by a certain number, could be quadratic. Notice the y's are all even. X's are going by 1. Jordan, we're on page 39. Please join us today. Question number 2. Mr. Strang, would you read that, please?
A rock is dropped from the top floor of a 500-foot tall building. A camera captures the distance the rock traveled in feet after each second. How far will the rock have fallen after 6 seconds? Show your reasoning.
Okay, so there's throwing a rock off of the top of a building. It shows you the exact location. It says, how far will the rock have fallen after 6 seconds?
It'd probably be on the ground.
500 feet.
Yeah, all of it, right? It's on the ground. So I would certainly say 500 feet. Travel the entire distance. Rock is on the ground.
Are those the exact same numbers?
Yes, they are. Question number 2. Jada noticed that the distance fallen are multiples of 16. She wrote down 16 times 1 would be 16, 16 times 4, 16 times 9, and so on. Then she noticed 1, 4, 9, 16 are all perfect squares. 1 times 1, 2 times 2, 3 times 3. It says use Jada's observation to predict the distance fallen after 7 seconds. Okay, assume the building is tall enough that an object drop would fall for at least 7 seconds. So using Jada's pattern there, what would be our equation? 16 times what?
49.
Yeah, 7 seconds would be 7 squared. So 16 times 49. If you have your calculator handy, give that to me, please. So 784 feet. Again, assuming your building is tall enough. B, write an equation for the function with D representing the distance drop. So following Jada's descriptions there, can you give me an equation?
D equals 16 times x squared.
Ooh, so close.
Or t squared.
Yeah. 16 times t squared. So 8 seconds would be 8 squared, 9 seconds would be 9 squared, and so on. Question 3 about Galileo. Samira.
Galileo Galilei, an Italian scientist, and other medieval scholars studied the movement of free-falling objects. The law they discovered could be expressed by the equation D equals 16 times t squared, which gives the distance fallen in feet d as a function of time t in seconds. An object is dropped from a height of 576 feet. How far does it fall in 0.5 seconds?
All right, so here is, yes?
I just have a question. What is the 16 in this situation? Like, is that like when that kind of like slope, I guess?
It's a constant. So there's a gravitational law that says how fast things
So
fly.
why is it in every single problem?
Because
Because
every time you drop something,
it
yeah,
always goes
they saw a pattern,
It's always 16?
always.
It's weird.
Yep. Now eventually it reaches a point where it can't speed up anymore. It's called terminal velocity no matter what you throw. It's like 180 miles per hour or something. Can't go any faster than that. If you jump out of an airplane, there's a certain speed, you won't go any faster. I don't know what that is off the top of my head, but it does bottom out at a
Why
certain
would
speed.
it be 16 if it's different objects that weigh different?
Because gravity's pulling on it the same.
Okay.
All right, so now back to the question. A little science there for you. An object is dropped from a height of 576 feet. How far does it fall in a half a second?
4 feet.
How do you know that?
Plug it into the equation.
0.5 squared times 16.
Yeah, 1/2 or 0.5. So 1/2 or 0.5 squared is 1/4. Yeah, it is just plugging it into the equation. 1/4 of 16 is 4 feet. That's exactly right. Okay, question number 2 from this part. To find out where the object is after the first few seconds after it was dropped, Elena and Diego created different tables. Elena said distance fallen, and Diego is doing distance from the ground. So what goes next to the 3 in Elena's table? How far would that thing fall 3 seconds into it?
144,
And 4?
256,
And our equation?
16 times t squared.
Yes, same as before. Now what is Diego doing?
Well, couldn't you just like subtract the numbers we just did from? Oh,
Yeah, so it is 576 feet from the ground, right? It's top of the building. 1 second later, he's subtracting the 16. Then he's subtracting 64. All from the 576 now. So 576 minus 144.
432.
576 minus 256.
320.
Okay, so my equation then, I'm taking 576 minus whatever I got on this side. Yeah, distance from the ground, so this is how far it fell from the top. So how are they alike? They're all doing distance. They're all measuring same time even. How are they different?
Diego's is more specific to the situation.
Yeah, Diego's is probably more specific. I'm probably concerned about how close I am to the ground than how far it fell. Right? So they are measuring two different things. Diego's might be better. If something's falling from the top of the building, I want to know how far it is away from me. This is how far it is away from the top. And completed, I guess we already did that. So that one is already done. All right, we're going to skip that Are You Ready and talk about just a couple things in that summary. Georgia's going to read the top paragraph of the summary, please.
The distance traveled by a flying object in a given amount of time is an example of the quadratic function. Galileo is said to have dropped balls of different mass from the Leaning Tower of Pisa, which is about 190 feet tall, to show that they traveled the same distance in the same time. In fact, the equation d equals 16 times t squared models the distance d in feet that the cannonball falls after t seconds, no matter what its mass.
All right, so there it is. There's D equals 16t, no matter the weight or the mass of the object. So then they go through and plot them. One is, again, distance dropped, and you can see what kind of shape that's going to make. And the other one would be distance from the ground. Again, this is the one that I would be more concerned about. How far is it away from the ground? And you can see what kind of shape we're going to have there. Okay, pretty self-explanatory from there, as long as you remember that equation. Take a look at your homework. Okay, short lesson today. Question number 1, circle the word all, please. All. 2 is self-explanatory. 3, which table? That one is multiple choice. One answer there. Question number 4 is not multiple choice. Okay, you can go ahead and write each one of these down, and you will circle which one is larger for each one. When n is 1, which one's larger? When n is 3, which one's larger? When n is 5, which one's larger? So that one is multiple choice as far as each other, but you can't just circle one of these 3. Okay, last page there, select all once again. Multiple choice for 6. And then the rest here are some review. 7, piecewise function. See how well we remember that from Unit 4? Remember, you're going to have different lines there. Watch out for open circle or closed circles. 8 is review. 9 is review as well. So look forward to seeing Samira's number 7. Maybe we'll even show it for the YouTube world to see tomorrow.